Hi guys, Zong here, back with another math video. I've had a request to do vector math, um, so let's get started. This is a question that I just made up, and try to like do it. Yeah. Okay, so today we're going to be doing vectors again, like I said. The other two times should get you ready for this question, and you might even be able to solve it on your own. It's sort of a practice. So let's just draw this out first of all. So you have a plane. Yeah. Well, let's have a graph because the graph will make it look easier, you know. Sorry. And the plane is traveling at a 360 kilometers per hour. And if you're dealing with speed here, usually speed and like what we had in vectors part 1, weight is usually the magnitude of the vector. So speed can also be used as a magnitude of vector representative. So if we have a speed of 360 kilometers per hour, that just means the length of our vector is 360 and the magnitude is 360, and a true bearing of 330 degrees. A true bearing is basically just the way people calculate direction. It's just if true north is 0 degrees, then a true bearing is just how many degrees it takes to go around here. Whoops. So like this is x. That's a true bearing of x, and this tells like what the direction is. So if there's a true bearing of 330 degrees, that means you do this. This will be 330 degrees. So it'll look something like this, but this is just 30 degrees. So that's the direction the plane is traveling. This is north. True bearing always goes from north. And yeah. So we have our vector, sort of. We know this is 60 degrees, thus. And the length is 360 kilometers per hour. And you just have to know when to say these things. You should be able to become fluent at like translating problems into like vector problems. It makes them a lot easier and a lot simpler. So let's do the same thing for the wind. The wind is blowing from northwest, which is this way, from this way, at a true bearing of 100 degrees, traveling at 30 kilometers per hour. So 100 degrees should be like around here. Oh, whoops! I should probably just do a line. It's only 30 kilometers per hour, so I'll make it a bit smaller. So this length is 30, and this is 10 degrees. It's starting to get a bit messy, sorry, but you have the basic picture. So ship is traveling this way, wind is traveling this way, and in reality, the wind isn't at like one point like the plane is. So the wind is actually like going like this, like this, like this. It's all throughout. So you can actually draw the wind from here, because this is the place where the wind actually affects the plane. Oh frick, still on brush. This is the wind where the wind actually affects the plane, is right here. That's where it's actually affecting the plane, and this is where the plane will be, somewhere around there, I guess. So if you want to find the true direction of the plane, the actual direction after you put the wind in, all you really have to do is find the addition of these two vectors, because the direction vector of the plane, and then you add on the direction vector of the wind with both their magnitudes added together, like 30 kilometers per hour and 360 kilometers per hour. And using this point, the new point somewhere around here, or we don't know, you can actually use the arc tangent, or just use some basic trigonometry to find the angle that's traveling at in relation to when it was beginning. And that's how vectors can be used in real life, and that's how you can apply vectors to physics, which I think is really cool. So let's just try to do that. To add two vectors, remember, if we have vector 1 is like x1, y1, and vector 2 is like x2, y2. It should be pretty self-explanatory. The new vector, or v1 plus v2, is just equal to x1 plus x2, y1 plus y2. So that's what we're going to do here. We have to find, so first let's find the equation of the first vector, the vector of the plane. So the vector of the plane, the magnitude is 360 degrees, and we know that from the y-axis, this angle is about 60 degrees. So we can just make a small triangle, so it looks something like this: 60, 360. And this, of course, we want to find this length as the x value. which is just going to be, if you apply some trigonometry, 1/2 360, and 1/2 is just cosine. Well, this is just cosine 60. And of course, it has to be negative because the plane's going this direction. So it's negative 1/2 360, and the y value is going to be sine 60 multiplied by 360, which is just square root 3/2 times 360. And that's going to be the y value. So y1, this is x1, as you can see, is x1. So our equation for the first vector is going to be negative 180. And if you calculate square root 3/2 times 360, you would get 311.769. And that's our first vector. So this is the plane. This is the vector that the plane is traveling at. Seems pretty straightforward. Just again, just plot out the plane on the graph using the speed as the magnitude, and then find the x length and the y length. And now we can find the vector of the wind. And the vector of the wind, we do the same thing. So we have a sort of like a triangle like this. This is 10 degrees. So we do the same thing. The x value is just cosine 10 degrees multiplied by what was it, 30 kilometers per hour, which is approximately equal to let me check my notes, 29.544. And that's positive because of course x is traveling in this direction, but y will be negative because the wind is going in this direction, which is in a negative direction in relation to y. So that would just be sine 10 degrees times 30, which is approximately negative. We have to make sure it's negative 5.2094. So we have our new the second vector, 9.544, negative 5.2094, and that's the wind. So putting this in effect, we can just add these two together. So let's get rid of some of the stuff we've done so we don't run out of room. Okay, so of course you add these two together, and if you do the calculations, you get V1 plus V2 equals negative 150.456. Yeah, it's just these two x1 and x2 values added together. And if you add 311.769 and subtract 5.2094 from that, you get 306.56 approximately. And this is the vector you have. From here, we have to find the direction of the plane, and let's just plot the approximate vector out. And remember, that vector actually defines like what this point right here is at, like this point. It's the it's the vector of the plane added onto the vector of the wind. So it's somewhere in the I think that's the second quadrant. Yeah, somewhere in the second quadrant, and we'll just find where that point is and get the direction from that. And since we're using true bearing, we should probably convert our direction into true bearing as well. So yeah. Anyway, so that's going to look something like, whoops, sorry, it's going to look something like, so this is 306.56, and this is negative 150.456. And to find this angle, you just need to take the arctangent of 300. Again, just some trigonometry. 150.456, and you get approximately 63.86 degrees, and that's what you get here. That's what this is. You have to convert it to true bearing. So if that's 63.86 degrees, you have to add on 270 to it. So that would be just 333.86 degrees if you add on 270. So that's what this is. True bearing. So yeah, we just solved the problem. I thought it'd be good to get some good vector practice on like just doing basic things and applying it to physics, because vectors is used a lot in physics and stuff like that. I think vectors is also used in calculus. We might do a calculus problem for the next part to spice things up. But till then, thanks for watching. See you next week. So let's list out all the multiples of 200. So that's just 200 times 1, 200 times 2, 200 times 3, 200 times 4, etc. Right? So if you take 1 over x squared of all of these, then you get 1 over 200 squared times 1, 1 over 200 squared times 4, 1 over 200 squared times 9, ... You get the idea. And actually, this is if you actually factor out 1 over 200 squared,